Hi, everyone. I'm Arjun. I'm a CS PhD student at Cornell, advised by Rachee. And today I'll be presenting our work about traffic engineering with probabilistic link capacities. So optical fiber enables pretty much all long-haul connectivity via both terrestrial fiber and transcontinental undersea fiber. And cloud providers use this scarce and expensive fiber infrastructure to provide high-capacity inter-data center links. And now I'll show you how cloud providers enable this terabit scale inter-data center capacity. First, we have our data centers, and they're connected by an optical link, which consists of a wavelength at a particular modulation format and at a particular region of the electromagnetic spectrum. In this case, it's at 1547 nanometers, and the modulation format is 8 QAM, which means that it can support 3 bits per symbol of the light wave. And however, even with the highest order modulation formats that are available today, a single wavelength can only reliably support gigabit scale data rates. And this is really intrinsic to sort of Shannon's limit. However, so how we would do this is that we would aggregate multiple wavelengths to create like a monolithic high-capacity link. And this is called a link aggregation group or a lag, and it's sort of the standard practice to deploy terabit scale capacity between data centers today. However, fibers exist in the physical world and are often subjected to bends and vibrations at points or along the path. This is an example of a fiber in our own lab setup, and you can see here a macro bend which arises pretty naturally. And so what we wanted to understand is what happens to the link under these ordinary fiber disturbances. And it's still unknown how sort of these disturbances would impact links, large link aggregation groups today. So to study this, we designed a hardware prototype of a long-haul optical link using our lab testbed, which is shown here on the right, which consists of an optical line system, 100 kilometers of fiber, and we built a lag with 3 constituent wavelengths, and I'll describe sort of the setup of what these wavelengths are on the next slide. And so we conducted 2 experiments in the lab that highlighted a new phenomenon, which we call wavelength-specific faults, and I'll describe what this means via the experimental results. So first, what we did is we took 3 different wavelengths at different regions of the electromagnetic spectrum that are used for optical communication, called the C-band. And you can see them in the legend at the top. And we basically aggregated these into a single link aggregation group, so they were sent over the same fiber. And we wrapped this fiber around a 3/4 inch cylinder, inducing a bend, a macro bend like the slide I showed you before. And what you can see here is over the course of the experiment, we can see that 2 of the wavelengths fail earlier on, in fact, the 2 that are at the further ends of the electromagnetic spectrum, and 1 fails a little bit later. And the link stays up sort of at the logical level until the last wavelength fails, right? And we also did this with different modulation formats. So now we use 16 QAM, 8 QAM, and QPSK for the 3 constituent wavelengths. And what we can see here is that over the course of the bend, the link actually stays alive completely because 2 of the modulation formats remain resilient while 1 of them fails. And so now the link stays up, but it's at reduced capacity when this 16 QAM wavelength fails. And so the key takeaway of this is that different wavelengths respond differently to the same fiber conditions, what we call wavelength-specific faults. You have links that are perceived as monoliths, but the link can actually exist in intermediate states because its constituent wavelengths behave differently. And these wavelength-specific faults change our abstraction of the WAN. Typically, we think of the WAN as a graph with data centers as nodes and links as edges with a fixed capacity. However, with wavelength-specific faults, edges now become discrete random variables that exhibit stochastic capacity, like the graph shown on the right. And so we were curious if this actually happens in the real world, so we collaborated with a large commercial cloud provider, and it turns out that they see this problem all the time. For example, the capacity of this production inter-data center link fluctuates frequently over a 1-month period, and there can be up to 40 capacity fluctuation events in a single 5-minute window in this cloud network. So how do we design WAN systems to be more resilient to wavelength-specific faults? This is the focus of our work, and we designed 2 techniques to tackle this challenge. First is HEDGE, which designs wavelength-aggregated links with capacity guarantees while still efficiently using optical hardware resources. And the second is HEDGE, which makes optimal flow allocations on this now stochastic network graph. So now I'll start off with HEDGE, and I'll first provide some intuition behind the lag design problem. So remember that we have our 2 data centers, and they're connected via a high-capacity lag. And our goal here is to provision a link for 400 gigs, but now we also want to guarantee that it provides at least 200 gigs 99.9% of the time. And we have one key decision to make, which is the modulation format of each wavelength in the lag. Our most reliable modulation format is QPSK, which can provide 100 gigs by transmitting 2 bits per symbol, and let's say that has a failure probability of 0.001. And QPSK requires a low signal-to-noise ratio threshold to sustain, which makes it more reliable, as you can see on the top right. Then we have 8QAM, which can provide more bandwidth per wavelength, but is riskier. So given that QPSK is up, 8QAM may still fail with 0.001 probability. And you might be wondering, why do I use a conditional probability here? And that's because these failures are not independent at all. 8QAM requires a higher SNR threshold to sustain than QPSK, so it will always fail if QPSK has failed, but that means it can even fail if QPSK has not. And finally, we have 16QAM, which provides even higher capacity, but has an even higher failure probability. So we could sustain 400 gigs on this wavelength by simply provisioning 200 gig 16 QAM wavelengths. And this satisfies, it meets 400 gigs with 99.7% availability because it requires the SNR to be high enough to sustain both QPSK and 8 QAM and 16 QAM. But it fails with 0.3% probability, which does not meet our availability target of 3/9 of availability at 200 gigs or higher. I could do something like this, which is very reliable. I could provision 4 QPSK wavelengths, which now means that I'm sustaining 400 gigs 99.9% of the time, and I fail with 0.1% probability. But while this meets availability, it's inefficiently using hardware resources. We're actually doubling the number of channels required to provision the required availability guarantee. And so what HEDGE does is it navigates this trade-off between capacity and availability. And you can see here the solution that HEDGE would output, which is that we can provision 2 wavelengths at QPSK to provide the resilience and the availability guarantee of 200 gigs, at least 99.9% of the time, while also not using as many spectral channels as doing a naive approach where we just provision with QPSK would. More generally, HEDGE formalizes this problem as provisioning Cmax capacity for the lag using the fewest spectral channels while guaranteeing Cmin capacity with a likelihood greater than or equal to beta. And again, our key decision variables are how many wavelengths to provision of each modulation format. And instead of writing an ILP, we can solve this intuitively by creating the abstraction of capacity states. The highest possible capacity state is if no modulation format fails, while any intermediate capacity state I occurs if modulation format I has failed, but lower order modulation formats are resilient. So we now have the probabilities of each capacity state, and so we should then provision Cmin using the highest modulation format that satisfies our availability target, which is achieved once the sum of the probabilities across all higher capacity states greater than or equal to I is at least beta. We use the highest modulation format among those to satisfy this constraint because it uses the fewest spectral channels. And to be as capacity efficient as possible, we can provision the remaining capacity between Cmin and Cmax simply using the highest order modulation format because it's not subject to any availability target. Okay, so HEDGE provides capacity guarantees to lags through intelligent wavelength aggregation, but this doesn't change the fundamental problem, which is that links still exist in multiple capacity states. So the next natural question is, how should wide area traffic engineering systems adapt? And so now I'll introduce HEDGE-TE, which is our TE method for routing on WANs with stochastic link capacities. Let's consider a toy network with 4 data centers and 4 links, as shown here. And while 3 of these links exhibit standard sort of binary states, where it's up or down at 1 terabit per second, link AC now exists in an intermediate capacity state of 400 gigs, 9% of the time. And now let's say that I want to route 1 terabit per second of demand from A to D. So how would I normally solve this on a network? I might do something like maximum flow by maximizing the throughput across all paths to serve this demand. And in this case, we have these 2 paths that are shown on the left. And our optimization is subject to the standard link capacity constraints and demand constraints. So I could be very cautious now, and I could sort of constrain my allocations by the minimum non-zero capacity on each edge. So now link AC's capacity constraint is constrained by 400 gigs. And so in this scheme, I could satisfy my demand by routing 1 terabit per second on the top path and 0 on the bottom path. And I could go anywhere up to sort of a 0.6, 0.4 split. I can't exceed 0.4 on the bottom path because I'm constrained by the 400 gigs in this cautious setup. So this seems great, but what happens now when I have 1.4 terabits per second? Now I could route 1 through the top path, and I'm saturating the network here by routing 0.4 through the bottom path. So what this means is I'm dropping 100 gigs of traffic 90% of the time when the link is actually operating at its provisioned capacity. So another sort of naive approach I could take is to be really optimistic. I could constrain now by the provisioned capacity. So I would treat the capacity constraint at 1 terabit per second on link AC. And so now I could do 1 and 0.5, satisfying my 1.5 terabits of demand. And I could, if I was running something like ECMP, this sort of naive approach would also output something like 0.75 and 0.75, which drops 350 gigs 9% of the time, right? So what we do instead is we run HEDGE, which is sort of trying to maximize the expected throughput of the network by penalizing by how much I might congest the network across different link capacity states. And a nice part of HEDGE is that we formulate it such that it grows linearly in the number of capacity states rather than in the number of network scenarios, which is actually an exponential function of the number of capacity states. And so here, the penalty is sort of how much I would congest the network in expectation. So it's the probability of that link state and the congestion in that link state, which is simply how much I've exceeded the link's capacity and retaining sort of a linear programming formulation. And so now I can guarantee that I'm always doing this sort of optimal 1 and 0.5 split, which guarantees that I'm always ensuring that I'm minimizing the amount that I would overcongest the network in these link capacity fluctuations below the provision capacity. And so I'll very briefly talk about how we evaluated HEDGE here across several cloud and ISP WAN topologies using sort of 10,000 TE iterations with real demand matrices and link states. And we define this key metric of availability, which is the percent of these iterations where we don't exceed any link capacities. And this is important because it sort of says how resilient our scheme is to overcongesting the network. And so what we do is we scale the demand matrix across iterations, and the goal here is to see what is the trade-off between throughput and availability. Because I can, as I scale the demand, I should be able to satisfy more throughput, but that shouldn't come at a huge cost of availability because now I would massively overcongest the network. And we can see that sort of we want to be in this top right corner of the Pareto frontier, and compared to a number of schemes in the literature, such as TVAR and RADWAN, as well as the naive schemes that I showed you before, HEDGE sort of performs optimally in this, expands this Pareto frontier. Another way in which we could think about this is we could have an oracle WAN, right? So now, anytime the capacity of a link changes, I immediately recompute the flow allocations, send these updated flow allocations to routers, and trigger protocol reconvergence. So this oracle WAN would be perfectly optimal because it's sort of adapting to the instantaneous state of the network, but it also incurs a high overhead because it has to adapt anytime the link's capacity changes, not just every TE iteration. And what you can see here is that compared to the Oracle WAN, HEDGE reduces the number of tunnels that are displaced by 622x. And what I mean by displaced tunnels is how many times I had to update the path weights for a particular path. And while sustaining nearly equivalent throughput. And remember, the oracle sustains the maximum throughput that's possible because it's able to adapt to the instantaneous state of the network. And finally, it's computable within milliseconds on a number of production WAN topologies. So I'm going to conclude with the broader takeaways of this work. And so while we have nice network abstractions in CS, the physical world is not so nice, and as we showed with wavelength-specific faults. And this is why HEDGE integrates stochasticity into the core of its design. To a TE or optimization person, there are two data centers connected by a 1 terabit link. And this simple view allows us to use elegant algorithms in CS, such as multi-commodity flow, to solve flow routing problems. However, to someone who works closer to the link layer, there's actually two border routers with two Ethernet links of 500 gigs each, and they're aggregated together to create this illusion of a link aggregation group. And to someone who is an optical engineer, we really just have two wavelength selective switches, or ROADMs, that are connected by a piece of fiber. And within this fiber, there are two wavelengths at different regions of the electromagnetic spectrum and at different modulation formats. And what our work showed is that essentially the sort of physical layer changes that happen at the very bottom layer propagate all the way up to and have consequences for how we design links and how we route on these wide area networks. So thank you, and I'm open for any questions.